And the topic is Chapter 4, Time Value of Money. So this is one of the most important things we have in finance is to be able to quantify the different present values and future values. So we're going to start with just an introduction to what time value of money is, and then move on to show some generic approaches on how to use the Excel functions and formulas to solve these types of problems. Then we'll go through some scenarios, and they will be in three different types of patterns. One would be a single payment, the second would be a series of identical payments, and the third would be uneven cash flows. Finally, we'll wrap up with some other comments on other variations we often see in this field. Let's start with something very simple. Let's say you have a choice of having $1,000 right now or wait 10 years for $1,000. What would you prefer? I think you all know the answer. The answer is we'll take the money now, right? So your instincts are correct, and that illustrates the time value of money. Now, the difference between an intuitive approach like you just had, like, oh yeah, I'll take the money now, compared to 10 years from now, is what is the quantified difference? Like, would you rather have $1,000 now or say $8,000 in 10 years? Now you're going to think about it a little more. This kind of quantification is what we do in TVM. So let's try a second one, which I think is also easy for you. Let's try this one out. So if you put $100 now in a bank and it earns a 5% per year interest rate, what is it worth in 1 year? That's a pretty simple one. You may not even need a calculator to do that math. You would say, okay, I put $100 in a bank. 5% of 100 is $5. So in 1 year, if I go back to the bank, I will have $105. And that would be the correct answer. That is the second one. So does that make common sense? I think that does as well. Now let's push your brain a little harder. Let's say you go to the bank, but instead of just taking it out in 1 year, what happens if you take it out in 2 years? Why don't you think about that for a moment, and I will go through it. And the question is it simply 5% times 100 times 2 years? So the total would be $110, or would it be something else? So take a moment. Okay, I hope most of you would think that, well, it's worth more than 110 because in that second year, I get to earn interest on my interest. In other words, I start year one with 100 and that grows by 5% to 105, but the second year, you start with 105, not 100. So 5% of 105 is $5.25. So you would actually end up at the end of year 2 with 110.25. And so that shows this notion that we call compounding. So I hope that common sense makes sense to you. And we'll go through now through some math. Okay, so congratulations. You've actually figured out, without knowing it, the formula for a future value. So let's just recap what you guys just did. First, we had this section here. So first thing we noticed is that 1 year, this was the easy one, we knew it was 105. The second year, we had this first term here, which represents 1 year's worth of interest, and then we multiplied that result times another factor to get to the compounding effect. So we ended up, as mentioned earlier, with 110.25. Here it is just showing formulas and numbers. Now, if we generalize it, we can actually come up with a very important relationship, which is this formula, which works for any present value, any future value, any interest rate, and any period. Here it's present value, and in this case it was $100, times 1 plus the interest rate, which is 1.05, to the n power. Now this n power relates to this notion of compounding. So if we did this calculation using this formula, you'll see, of course, we end up with the identical number. That 100 times 1 plus 0.05 or 1.05 to the second power is 110. So that formula validates kind of your notion of how bank interest would work, which again validates your notion that money today is worth more than money a few years from now. In this case specifically, you'd be indifferent taking $100 today or $110.25 if your sole objective were 5%. All right, so let's try the next one. Since we know this formula, we can then say and notice that in the algebraic equation, we could solve for PV. So if we simply solve for PV, we end up with identical terms but reordered somewhat, such that the present value is equal to the future value divided by 1 plus the interest rate to the n power. It shouldn't be too scary because this formula is derived from the one we just figured out previously. So these are the two core formulas in time value of money. Next, I'm going to talk about the three types of cash flows that we normally confront. And depending on the cash flow, we use a different technique to solve the problem. So the first is what we've just been doing, and that's called a single payment. So that's just putting a certain dollar amount in now and waiting for what it's worth later. Or the flip side, if you got money 10 years from now and it's $1,000, what is the equivalent and what is it worth today? So this can go both ways. PV to solve the FV, FV to solve the PV. So that's a single payment. The second are series of payments. We call these annuities. And there are many examples of annuities. The thing that has to be the case is it has to be an identical payment. So you can't have payments that go up and down or maybe skip a year now and then. It has to be regular identical payments through the entire term of that particular series of time, let's say. So examples, would you buy a house and you need to borrow money called a mortgage to repay the loan over 30 years. That's a perfect example of an annuity. It is a regular set of payments you make monthly until the end of the term, in which case you own the house. Third type of pattern is uneven, where it's lumpy. It could be zero some years, positive some years, negative some years. And this is more example of like an investment. And the example that I would cite here is, let's say you buy an apartment house in San Francisco. Your initial cash flow right away is to pay a lot of money. And then each year as the owner of the building, you will get cash flow. Some years could be high, some low, some may be negative where you have to make improvements to the house and you're ending up putting in more money. And at some point out in the future, you sell the house or sell the apartment and you get a big, hopefully big lump sum of cash when you sell the house. And now you have this very uneven set of cash flows. And we use time value of money concepts to evaluate those cash flows and figure out, in this example, whether the apartment is a good deal or not to be purchased. So these are three patterns that we will see in cash flows. And depending on the pattern, we use different tools. Good. So next I'm going to show a picture. It's often good in time value of money problems to visualize it, and sometimes it's pretty obvious and you may want to just take a shortcut and not do it. But I find that it's kind of worth sketching it out just to see what it looks like. So here's just a generalized picture of multiple cash flows where we are trying to figure out the present value. Here we have time being signified here as 0. So right here, we're at time 0. So time 0 in time value of money talk is today. So today is time 0. Next, we have cash flows that are for time 1, time 2, and time 3. So these three cash flows are at the end of those years. Then we sell an item at the end of year 3 or the beginning of year 4. So those actually compress as if it were done on the very last day of year 3. Just in realistic terms, the last day of year 3 is very similar time-wise to the first day of year 4. So as a matter of convenience, we normally collapse those two into one bigger cash flow at the end of year 3. So the idea of a PV says, how if we take that cash flow, bring it back to today, take this cash flow, bring it back to today, and do it for each of the cash flows, and we end up now with the 4 different cash flows that now are all in today's dollars without any kind of blur because of time. And we end up with this very important notion of the net present value, which is the sum of all the cash flows in that particular pattern. If we had a price to buy this investment, let's say, the NPV is below, which means let's take the present value of all the money you get and subtract from that the cash flow to buy that particular investment. And if the NPV is a positive number, that means that the money you get is worth more than the money you pay, which is a good thing. If the NPV is a negative number, that means the money you get is less than the money you pay, and that would not be a good investment. So that's just a very simple example of how we use present value and how net present value is the most useful approach to doing evaluation of an asset. Next, we can go the other way. In the previous example, we brought everything to today, time zero. But what if we want to know what something's worth in the future? In which case, we're pushing everything out forward instead of pulling them backward to today. So here we would put down some money, and let's say we invest $100 today. And then a year from now, we invest $105. And year 3, we invest $110. And year 3, we invest $7,000. So in this case, we go the opposite direction. We take this cash flow of 0 and say, how much will it grow as of this point in time? Then we take this cash flow at the beginning of year 1, and we say, how much will that grow for that particular period? In this case, the future value equals the sum of what everything's going to be worth out at time 3. So that's a generalized picture of future cash flow, where money flows at a certain time, and then you sit and wait, let it grow, and see it accumulate to some later point in time. So that's this notion of future value. Here's a general approach to using TVM problems, and then we'll jump right into Excel. The first step is to determine the cash flows. It's very important to get both the dollar amount correct and also when the money moves. Since time is money, it matters whether you get it in today's terms or year 1, year 2, etc. So get the dollar correct and the timing. Second is to determine what's the interest rate. Sometimes in calculations we call it the discount rate. Or in your bond calculations, it was equivalent to the yield to maturity. The third is I always like to draw a little picture so I could visualize what the money flow looks like. That's just for my approach to testing the reasonableness of the solution. And then the last step is to do the actual calculation. Now there are 4 ways to do it. One is this old-fashioned way where we use present value tables. We have them in the book, but I haven't used them in years, frankly. There's far more efficient ways to do it. Second is to use a regular calculator. A regular 4-function calculator could even do the trick for most calculations. I don't recommend that either because it's quite tedious. The third is to use a financial calculator. And for many years, we taught finance where we required students to buy a financial calculator. Now, if you want to learn a calculator, I welcome it. I happen to like calculators, but it's not something I'm going to push as our primary tool these days is Excel. So if you want to learn how to use a financial calculator, go ahead and buy one. I would recommend a Hewlett-Packard 10 or 17, 10B2 or 17B2 Plus. Those are my favorite calculators. I could explain why if you're really geeky. And if you want to skip the financial calculator, it's fine. We're going to use Excel. So I'm going to focus our teaching on Excel, but I just wanted to point out that there are multiple ways to solve time-valued money problems. So next we're going to look at some scenarios using time-valued money, but first I'm going to give you a little Excel lesson.